Welcome everybody to the NSERC PermafrostNet seminar series. Today's seminar is by Usman, Iqbal, Ahmed. Usman is a PhD candidate in the SAR lab at Simon Fraser University, Burnaby, under the supervision of Dr. Bernard Ravis, supervised by Dr. Fabrice Calmels from Yukon University. SAR lab is focused on research related to airborne and spaceborne radar techniques and applications. Usman is undergraduate and master's degrees both in avionics engineering in Pakistan, with a primary research focus on radars in general and SAR in particular. He started his PhD research with Permafrost Network in 2020, where he realized the opportunity of using the SAR Lab's airborne SAR and optical system to enhance change protection for its application to permafrost monitoring. He is collecting biannual airborne SAR and optical data along a 12-kilometer stretch of Alaska Canada Highway near Burwash Landing, Yukon. He's developing his methods, which are then flexible to be used for monitoring other high-value infrastructure built on top of permafrost. And today he'll be presenting some of the results from his research.
Thank you, Tristan, for the introduction. I'll formally start with my presentation, which is on the topic precise change detection with airborne interferometric synthetic aperture radar and optical photogrammetry data and its application to the active permafrost regions. I am a PhD candidate at SAR Lab Simon Fraser University, working under Theme 2, under the supervision of Dr. Bernard Ravis at SFU. First, I will give you a brief overview of the research. Please bear with me with some of the technical terms that are being used. I will introduce them later. But for now, just the overall overview of the research is that we are using an airborne SAR and optical system, which is experimental. And what we are trying to do is do linear infrastructure and permafrost monitoring, as well as change detection. Techniques that are being employed are the optical structure for motion and synthetic aperture radar interferometry. And the area that we are targeting on the spatial scale, it's like a few kilometers, and then temporal scale depends upon the application. It can range from days, months to years. So my whole PhD research is focused on one main theme, that is understanding the role of the airborne platform's precise position, its motion and orientation, and how does it manifest into this optical structure for motion outputs and the interferometry outputs. What we are doing is long-term change detection in a focused area of interest with the methods which are repeatable, extendable, and flexible, and can be adapted to different regions. And the primary area of my research focus is the Alaska-Canada Highway stretch near the northern part of the Kulwani Lake. First, I will introduce a few terminologies which will come over and over again in the presentation so that everybody is familiar with what I'm talking about. Starting from the term synthetic aperture radar. And the term itself originates from the term radar, which is radio detection and ranging, and is primarily sending out radio waves to the target and then timing the return from the radar to the target and back, and then detecting how far is the target. So that's how the name comes from, which is radio detection and ranging. One major problem with radars is that it suffers from the resolution, which is limited by the beam width of the antenna, and then which in turn is limited by the length of the antenna. And for the airborne as well as for the spaceborne sensors, you can only put a limited size of antenna up there due to power limitations and size limitations. So you're limited with in terms of the resolution. Here I call it as RAR, which is the real aperture radar. And what we do, we use digital signal processing techniques to synthesize a larger antenna, which basically makes a resolution synthetically big. And that's how the name of the synthetic aperture radar is coined. This is a typical SAR geometry where SAR sensor is inherently oblique looking. It looks at an angle, mainly because if it be looking right down the sensor, it won't be able to distinguish between ranges. And the primary technique that is being employed by the SAR is the ranging technique. So once you look at an oblique angle, you can distinguish between the near range and the far range targets. And in comparison to the optical sensor, a SAR is an oblique looking sensor, whereas an optical sensor is generally looking straight down. And a radar or SAR is distinguishing targets in range, whereas an optical sensor is distinguishing targets in angles. So here you can see that both the sensors, if combined together, provide complementary information, which can be combined for enhanced information about the targets. Moreover, the SAR sensor is active, it has its own energy, whereas the optical sensor depends upon the sunlight. And also it's occluded by like clouds and other stuff. And SAR sensor can see through clouds. It's an all-weather day and night sensor. Some comparisons of SAR and optical images is given here. On the top image, you can see the SAR image on the left and the optical image on the right. They both look like images. You can say like the SAR image is a black and white version, but if you look into it in more detail, you can see more because the SAR sensor or the radio waves can penetrate through foliage and through some of the materials. So you can see through them. And it also interacts with the surface. You get more surface information, and based on the surface properties, the scattering or the image properties look different. There are advantages and disadvantages of SAR in comparison to the optical sensor, but we are targeting to combine both the informations to get enhanced information here. Coming over to the interferometric SAR, so as the SAR sensor is basically radio waves traveling in air, you have the phase information available with the wavelengths that are transmitted. Utilizing that phase information from two similar acquisitions, you can do interferometry, which is the phase difference in the two similar acquisitions. And interferometry can be of different types. Single pass and repeat pass are the main major categories. Single pass is where the two antennas are mounted on the same platform in a long track or the across track position. Both of the types are used for different purposes, but primarily my target for this research as well as for this presentation is the repeat pass interferometry, where you acquire images from similar geometry and then utilize the phase difference of the two acquisitions and transform that into change direction. What we are trying to do in a repeat pass interferometry, so the phase difference that is measured from the two similar acquisitions consists of various components, as shown in this equation as well on the top right. So you can basically model different components of the phase, and what you are concerned about is, for example, in this application, we're concerned about the motion. So we would subtract all other contributing factors from the phase, and whatever would be left would be the motion or change that would be there between the two acquisitions. On the other hand, the optical sensor that we are using, we call it FODAR, and the term originates from the photo detection and ranging. It is a term coined by Fairbanks FODAR, and it's merely a photogrammetry technique which employs structure for motion at its heart. It's slightly different from conventional photogrammetry, where we're using commercial off-the-shelf camera instead of sophisticated photogrammetric imagers. Although the photogrammetry has evolved quite a lot, and then nowadays this UV-borne photogrammetry is very common, which does not use this sophisticated photogrammetric imagers, but this is still in use in some like high-end applications of the photogrammetry. And we're also using onboard survey grade GPS, where we are georeferencing the images that are taken instead of doing ground control points, which eliminates the need of like going into the field physically and doing ground control points. And then you can still achieve LiDAR-like accuracy in the DEMs that are generated from the photogrammetry. And typical outputs for our system is the DEMs. We could generate orthomosaics. And one interesting factor that we have figured out from our system is the motion refinement capability of the system. So mainly, but as I told you initially as well in the overview, that my primary target is to focus on the motion, attitude, and the location of the sensor and how it manifests into the outputs. So in a typical SAR, it's not very critical in spacebound because in space, there's not much air, there's not much perturbation, so the orbits, the satellites are very linear and very smooth. But in case of airborne, so the aircraft moves quite a lot. It's quite nonlinear track. So if you don't compensate that motion, because the primary assumption for the synthetic aperture radar is a linear track. So if you deviate from the linear track and if you don't accommodate that motion, you get defocusing in the worst case. But this focusing of the SAR is much more forgiving, where if you compensate the motion to a certain degree, you would still get pretty well focused images, but it manifests into the phase of the image. So once you do interferometry, as shown in the bottom figure, you see these kind of weird patterns or stripes as you do the interferometry, and this is basically the remnant motion artifact if you don't compensate the motion properly. In photogrammetry, the heart of the way we are using photogrammetry, the heart of the system is basically the precise location of the images. If you don't determine the precise location of the images, then the accuracy and the repeatability is not worth it. What we are trying to do is utilizing all the available sensors on board, like IMU, the GPS, and a local differential GPS station, as well as we have our system in different configurations, the radar system. So we utilize a long track interferometry also to come up with more precise and more enhanced information about the position of the sensor so that we can improve the results of the interferometry as well as the photogrammetry. So after looking at all this, I would reiterate the research objectives here, which is using the 4-DAR block adjustment parameters to enhance the platform trajectory and attitude knowledge for improving the airborne SAR interferometry. Whereas on the other hand, we are also trying to develop direct and indirect, like using the outputs of the photogrammetry as DEMs and the SAR images itself, and indirectly using interferometry and improving the trajectory information to create a linear infrastructure and permafrost monitoring applications from the systems. The system that we are using for the radar, it's a tri-band system, X, L, and C band, whereas our primary focus in this research is the L band component of it, because the main reason is that the L band has a wider beam width, and I'll show you in the later slides how that basically helps in sort of doing the change detection as well. And also on the bottom left figure, you can see the installation or the configuration of the system, the way they're installed. On these white patches are the L-band antennas, where the X and C-band antennas are at the bottom of the belly and of the aircraft. And then there's a hole in the belly of the aircraft from where we are installing the camera for the photogrammetry. Our optical system, or the 4-DAR now, is basically consists of 4 major components. One is the camera itself, which is Nikon D850. And we have the intervalometer, which synchronizes the flash events of the camera into the IMU stream. And then later we can differentially process the IMU and the GPS data and come up and basically extract the precise information of the camera locations. And then we are processing all the data through Metashape. Another difference of our system from the conventional photogrammetry is we are looking at an angle, and that is mainly to enhance the coincident optical and SAR footprint, because SAR is by default an oblique looking sensor. So we are operating our photogrammetry system in an oblique configuration as well, so that we have more coincident swaths of the SAR and optical system, and this gives us additional fusion potential as well. We don't have to do like additional flying to cover the radar swath with the optical system. And this is the area of interest that we are targeting. Some of you might be familiar with this region. So Silver City is our base station or our base camp from where we are doing all the flying. And this area of research, or the area of study, is this linear infrastructure, or the Alaska Canada Highway stretch of around 15 kilometers from Brewers Landing to like somewhere past the Quill Creek. We were initially studying the western part of the lake, But after talking to different folks in permafrost, we discovered that this region does not have continuous active permafrost underneath, so we moved to the northern part, which has more active permafrost layer underneath there. Why are we targeting the precise motion of the platform? If you look on the top right figure, these concentric circles, and the center of the concentric circles is the planned flight path. And this shows only one of the collects or of 1 minute, and you can see how much the aircraft deviates from its mean or the planned path. So this is the deviation within 1 minute, within one of the collects that we do for our system. And this is mainly because the aircraft that we are flying with is this one on the left, which is a lightweight aircraft and has much more nonlinearity in its flying pattern because of its lightweight. In comparison to this, once we look at some of the research papers that are being done in airborne interferometry and SAR systems, like FSAR, AirSAR, and UASAR, these are bigger, stable platforms, and have even being bigger and stable platforms, they still have like multiple IMUs and multiple GPS installed on the aircraft for obtaining this like precise trajectory information. For our 4DAR system, as I talked about, the typical outputs are the orthomosaics, and some of the examples are given here. So orthomosaic and the DEM. And the accuracy or the spatial resolution that we can achieve is around 10 centimeters. It also depends upon the flying height, but we are generally flying lower to achieve higher spatial resolution. As most of us, I guess, are involved in some sort of field work, and we all know that the field works don't go as planned. So there are always like ifs and buts and like problems with the field campaign. So our journey is similarly has been problematic so far. As we have evolved quite much over the time, and now our system is like much more professional. All the information that we have lost during our past campaigns, we have now in a state where we can tell during flying if there is anything going wrong with the system. So for example, initial problems were that during COVID, we were not allowed to do field work in winters, so that cost us some loss of data in terms of analysis. Whereas there was a system upgrade that was done in 2021, and that led to some kind of software bug, which also led us to acquire data at different heights. And this was mainly because we're right at the boundary of the 60-degree latitude. And as you go past 60-degree latitude, so the DEM posting changes. And that was not accounted for in the software. So we were sampling into the DEM at a different location that we were supposed to be in. So that led to us flying at different heights, and the interferometry was not possible for those acquisitions between different years. Although photogrammetry was possible, but we had DEM repeatability issues, which I'll talk about in detail in the results section. Then later on, there were certain problems. We also discovered through our journey so far that if we don't have differential processing, the PPP processing, although it's said to be pretty precise, but for our purposes, where we need extra accurate information about the aircraft trajectory. So PPP, we found that it is not as precise as differential GPS processing. And the worst case scenario was in 2023, we had a crash landing of the aircraft as well. But we were all safe, and then we were able to fly into a different aircraft this year. Going over to the results section, this is the processing chain. I don't want to talk about it in too much detail, but the primary focus here that I'll again bring to your attention is basically the image association with the camera positions. So this is the most important part of the 4DAR processing chain, where if we don't associate the camera positions properly, and if you're repeating the data sets over and over again, and then the camera positions are not properly associated, you would get repeatability issues. And if you don't have the DEM repeatability, you cannot do a change detection. So you have to have the accurate DEM like positioning or georeferencing so that you can perform a direct difference and as it could be as easy as a direct difference. So initially, once we installed the system in 2020, we did some like validation tests where we did some flying over the airstrip and formulated the DEM. And then we also, by virtue of operating the radar, we installed some corner reflectors on the ground, and we also surveyed them. So we took that opportunity of surveyed corner reflectors as ground control points there. And then we assessed the performance of our system against those surveyed points. And we found that, first of all, we tested our system in the straight looking down, the conventional photogrammetry way. And then we also did the oblique looking fashion. And we compared the performance of the system in the oblique looking fashion. And we found that it's not that off. It's slightly off in high rise buildings, but in our area of interest, there's no high rise buildings or anything which is like height, which has more height. So our oblique looking photogrammetry would work as good as another looking one. And we also compared our system against the Tandem X DEM, which is, I would say, the kind of global standard for now. Nowadays, that is the most accurate DEM that you find around that region. So we compared it against the Tandem X. We compared the system against also the reference system, which was from the Fairbanks FODAR. So we flew both the systems together and compared our performance against the reference system as well. So once we established the accuracy of our system, we also looked into the micronavigation potential for our FODA system, where once we input the camera locations and we do the photogrammetry processing, as an output, we get the estimated locations, which may differ from the input locations. And that could give you additional information about the motion compensation potential that I was talking about. So we could use that motion refinement into the SAR and InSAR chain and come up with more precise InSAR or interferometric SAR outputs. Looking at the initial interferometry results, so this is one of the orthomosaics and the SAR images of the same airstrip that we fly from. I won't go into detail of this, but the final result on the top right, you can see that there are these fringes or these like stripes. The horizontal direction is the range direction, and the vertical direction is the azimuth direction, the flying direction. So you see these stripes in the range direction, and these stripes are what we believed and we still believe basically is the motion compensation artifact. So if you don't compensate the motion properly, you get these kind of artifacts in the phase. And these images were acquired within an hour. So ideally there should be no change, and the phase or the final interferogram should be totally flat. There shouldn't be any patterns in there. So, and also I've categorically mentioned here the range Doppler processor. So there are various types of SAR processors, but we have looked into range Doppler processor and a time domain back projection algorithm based processor. The range Doppler processor is the frequency domain processor. There are certain limitations of it. I would talk about it in detail as well as we go along. Whereas the time domain back projection algorithm incorporates the sensor positions in a more accurate fashion as compared to the range Doppler processor. Once we had established our 4-hour system performance and accuracy, we moved on to the area of interest, and the data sets that we collected, we tried to compare it with each other. Here, the comparison is shown between one data set that was taken in April versus one that was taken in August. And we found, we assumed that, and as I've advertised it as well, that we have eliminated the use of ground control points, and the absolute georeferencing of the images would help us georeference the DEMs, and they should be accurate, and we should be able to just like directly difference them, and then we should be able to see if there's a change going on. We found out that this is not as reliable as we thought, and there were trends and there were biases between the two acquisitions from the two seasons. And we were like, what could be the root causes of this. And we started looking into what can cause this and how can we improve our results. So we thought about possible problems after looking at the initial interferometry and the photogrammetry results. So we thought, because our original test site is around 60 kilometers away from the differential GPS station that we are using for the differential processing. And as we move away from the differential processing, it's a known fact that the accuracy of the GPS positioning or the differential solution degrades as we go away from the GPS, the differential GPS station. So as the site is 60 kilometers away, we speculated that it could be because of the differential processing accuracy loss. And in the InSAR artifacts, we were looking at the range Doppler processing outputs, which is a frequency domain algorithm and uses a mean track to process the data and then compensates the motion to that mean track, and does it in frequency domain. It's not super accurate in terms of incorporating the motion of the platform. It's very good for the spaceborne sensors, but not as good as it should be for the airborne sensors. So we thought like maybe switching over to the time domain back projection algorithm might help. And also if we could utilize the 4-dart block adjustment or the motion compensation outputs from the 4-dart processing and improve the trajectory information and use it as a feedback and improve the interferometric results. So these were the few hypotheses that we made. And then the solutions that we proposed or thought of is basically for the improving the InSAR, switching over to the TDPP algorithm. And if there are still some remnant motion artifacts, so we can use some post correction scheme, which is data driven, to correct it. And for the 4-dart results, we thought of carefully planning an experiment where we could possibly install a local differential GPS station, do some ground control points for validation purposes, and also have some control changes in the area of interest, which mimic permafrost-like changes, like creating a snow heave or maybe digging a snow pit to mimic some kind of permafrost change in the area. Based on the proposed solutions, we crafted an experiment where in the area I installed a differential GPS station and surveyed certain ground control points, which were obvious. There was a borehole in the area, which was being maintained by Yukon University's research center, as well as there was some weather station which had clear markers which I could use for ground control points. So I surveyed those points. There were total of 10 ground control points that I surveyed. Extended our airborne profiles up till the borehole so that if we continue monitoring the borehole area, we could use some of the borehole data to maybe validate it in future or validate our results as well. And also on the bottom left, as I've shown, so I created one snow pile of 1 meter height and then surveyed it properly. And then in another area, I dig a snow pit, which also I surveyed properly so that we could use that as validation purposes. And while I was sitting in the parking where I installed the ground control station, and let me go back to the previous slide. What we did was within the same day, we did 2 simultaneous collects. Basically, did one set of data collection and repeated this data collection again at the same time, just as we did previously for the InSAR data, so that we could do the InSAR and 4-dart repeats and see if we can get the required accuracy in the results. And then we did another collect on a separate day, which was 4 days apart from this day, where during those collects, I did these changes of creating the snow pile and the digger snow pit. And this is where, while I was babysitting the differential station, so within the 2 collects on the same day, I just moved the car from one place to the other. That was the minimum change that I could create there, and just wanted to see if we could detect this much change in the 4-dart outputs as well as in the InSAR outputs. On the left is the SAR image of the 2 collects, where you can see these bright points is the car in the parking and on the entry to the parking, and on the right is the optical results for that. So once we did the FODAR results, and these are just the overview or the just the outlook of the results, the orthomosaics and the DEMs. And the 3 points that are highlighted as point 1, point 2, and point 3 are the ground control points that were done along the highway. And these red circles, the bottom red circle is the point where the differential station was installed. And the top left red circle is basically where the snow pile was made. So once we looked at the difference of the DEMs for this area, so after processing it with the local differential station, so we could see that these 2 points appeared like as we expected. So our suspicion was probably right that the differential GPS accuracy is causing the repeatability issues. So we could achieve what we wanted to achieve with this one, where we could see that once we difference the DEMs in this region, so the curve from where it moved to where it moved were clearly visible in the difference of the DEMs. For the other change that I made where I made the snow pile, it was 4 days apart, and then the problem here was mainly there was significant warming in those 4 days, and you can also see from the orthomosaics that it was the snow melt on the roofs is quite obvious. So these kind of changes in a snowy environment is not a good data set for interferometry, and that's why we didn't get like really cool results with the interferometry, but with the FODAR, we were still able to see some kind of change there in the area of the snow pile, which was cool for like when I looked at the previous results and in comparison with that, when I looked at these results, I was super happy that we are able to achieve the accuracy if we install a local differential station in the area. Going over to the InSAR results, on the top 2 are the SAR images for the same day, the 2 collects, and then this area, if you can see my mouse, is the area where the car was parked. So you can see a bright spot here if it's visible, and then these are the 2 collects where I move the car from one place to the other. And at the bottom is the interferogram, which doesn't look great by any standard. So we thought that the TDBP, or the time domain back projection algorithm, would improve the interferometry, but apparently not. It wasn't great. Then we also thought about like doing some post correction method to improve it. If we go to the focused area, this is some crop of the same image focused on the parking where the car was moved from one place to the other. And this is the interferogram, the center one. On the right next to it is the phase screen that we estimated from a scheme that is called residual motion estimation. And it basically utilizes different squints to process the data. And then from the different squinted processing, we can estimate what the remnant motion errors are. And then we can estimate a phase screen and we can post correct it. And on the most right is the corrected interferogram. You still see some artifacts in there, but at the location where the car was moved from one place to the other, we could bring that out pretty clearly as we were able to see it in the FODAR DEMs. So in the interferometry, we can reach that accuracy where we can see that change occurring, which is pretty cool for somebody who has dealt with airborne interferometry. I would say it's awesome. I don't want to brag about it, but it is really cool where we could see the interferometry changes. Once we were doing this airborne, and initially when the COVID occurred and there were restrictions on the field campaigns, we also looked at some of the spaceborne alternatives. Although when I said in the initial overview that the airborne data is flexible, there I categorically mentioned flexibility because the spaceborne sensors would have their own prescribed orbits, and you cannot change that. With the airborne sensor, you can always go to an area of interest and fly according to, like for the spaceborne sensor to work perfectly for your case, as the most of these spaceborne SAR orbits are north-south, so your change has to occur in east-west direction to be measured by the sensor. And you have to be very lucky that your infrastructure is north-south or east-west, and then is perfectly aligned with the SAR geometry, and then you can see those changes in there. But we did some spaceborne SAR data analysis as well for interferometry change analysis. So what we try to do is we also try to acquire RadarSat-2 data, and we were able to put in the request, and the data is being archived, but it still is not available right now, as of now, for our analysis. And there are some admin issues related to that. But on the other hand, Sentinel-1 data, which is freely available, so we used it 2 years of data, which is worth 58 images, and did some homogeneous distributed scatter interferometry, which is an advanced technique, and basically looks at some of these scatters which are homogeneous over the time, just like some, you can say, a rock glacier or some infrastructure like roads would be a good homogeneous distributed scatters in this case. And then we did some time series analysis for the line of sight deformation. So I would share some of the results with that from that research. We also modeled the daily temperature data, and then did some very basic vertical deformation estimation from there, which is, I guess, square root of degree days of thawing and freezing, cumulative degree days of thawing and freezing. And we use that in the network inversion as an estimate. And we followed this full InSAR processing chain to estimate the line of sight deformation. This is the overall image that was used, which is quite huge. It's like 250 kilometers by 200 kilometers. It contains from Silver City to like some portion past Whitehorse. And we used one subset of it and then subsets of that subset to do the interferometry analysis, because otherwise the data gets like intractable. It's like super huge, and then gigabytes and gigabytes of data, and it's hard to track of it. So one of the subsets that we processed was near the Silver City airstrip and some portion of the Alaska-Canada highway as well. On the top left is the Google Earth image of the area that we looked at. And then some of the candidate points, these red dots on the rightmost figure are the candidate points that were selected based on their homogeneous distributed scattering over the 2 years. And then we did some deformation analysis. This is, if somebody is familiar with this area, must be familiar with the name Sheep Mountain. So this is Sheep Mountain. On this edge of the Sheep Mountain, the eastern edge, so there's a rock glacier. And these 2 points are shown here, and the trend for these 2 points. So for the rock glacier, we were able to see that the rock glacier is moving down, or is deforming at a rate of around 10 millimeters per year. And also you can see some wiggles in there, which is the seasonal change of the freezing and thawing. And also on the road, we could see that the road is moving up. But this is not validated. So we need to validate this against some ground truth. This is just an preliminary analysis. We are looking into some kind of validation for this and see if this can be extended to other regions. In future, I'm targeting to improve the FODAR work by detrending the data from the past acquisitions, as I showed you that there were trends in range and azimuth, or in north and south, and there were biases, so we could detrend it and see if we can still make out some kind of time series analysis from the FODAR data. And for the airborne, we are still in the process of incorporating the motion refinement that we extracted from the FODAR sensor and incorporate that into the InSAR chain and see if that improves the results further. Also, for the spaceborne, we need to verify the findings that we have extracted from there against some ground truths. And in the end, I would target combining the results from the InSAR and the SAR, InSAR, SAR, and FODAR outputs. Because in certain areas where InSAR is applicable, that can only detect changes which are not like big changes because the area has to stay coherent. So if there is a big washout due to some flood or something, you won't be able to see that change in the InSAR. But FODAR can bring that out. So combining the FODAR and the InSAR outputs might lead to better change detection outputs or the change maps. In the end, I would like to acknowledge the contribution of Permafrost Network, the CFI in funding our system itself, PCSP for enabling us to do the fieldwork, and Fairbanks FODAR for their support in the FODAR system. I thank you all for your patience with, and now the house is open for questions.
I have a question for Usman.
Yeah,
so you didn't comment on that, but the amplitude images of the airborne SAR, I mean, they clearly also showed effects of this motion, right? So you get the bright and dark.
Yes.
And we never talked about this, but do you have any ideas? I mean, you're not in charge of writing that SAR processor, but I mean, you can still inject ideas as it's other students writing that. Like, there must be a way to clean this up somehow so that the amplitude of the SAR can also be used in a change detection. Do you have any thoughts on that?
Yeah, I would like to discuss that with Jeff because Jeff is the student that is working on the time domain back projection algorithm in our lab. I'm stepping on the shoulder of the giants in this case. I'm using his processor to get the outputs. So yeah, we could talk about it, Bernard, and then I guess there could be, because we have seen that JSON has some sort of correction where the images, sometimes they do show these kind of stripes, but mostly they do look much more like compensated for these kind of artifacts. They can be
compensated. It would be nice to be able to use, because I mean, obviously it's not so easy to get these interferometric changes. I mean, they're great, but they're not always there, right? If you take an image and you have the amplitude, you have the SAR image, it would be nice to have that sort of absolutely calibrated, that you can also measure change with that. It's just something that occurred to me suddenly when I saw all these stripes.
That's a great idea.
Hi, Usman, it's Tony. I'm just going to send you in, I don't know whether you were aware, you probably were, but there's another rock glacier in the Slims River Valley that might also be in your area. So I just sent you the coordinates, but did you have a look at that one too? I mean, I think having, big geo things that are moving, that are moving differentially relative to the surrounding area is a great experiment, right? You didn't have to start them. They're just doing it for you.
Yeah, I know. Like there is, right, and like on the other side of the Sheep Mountain, there is a rock glacier, and we have been imaging through the airborne sensor as well. And in the spaceborne data, it should be visible. I just like prop one subset of the data, which unfortunately didn't contain that specific rock glacier, but that is possible.
It's pretty close. Well, I mean, if you go back to show me your figure again, the one where you have the map. Because I was just looking it up.
You've been there. Like I led them there during this campaign. They got
this year we walked to that region. Yeah,
it's that one.
It's basically down here somewhere.
Exactly. And I'm just trying to see when I compare that to whether
it's basically here, kind of like in this Google Earth image. It's here.
It would just be on the edge.
Just
no,
on
it's
the
a
edge,
little bit. It's a little bit further away. It's just off the bottom left hand side.
Yeah, I might have a better image.
But it's a different. I mean, it might. The interesting thing about that one is that obviously it's advancing, but it's almost flat. So you might get
it is almost flat,
kind of a different signal from it compared to the one that's on the slope to the west of Kluwani Lake that you mentioned earlier. And also this one is almost covered in trees, whereas the other one is not. So
that's
just
true.
For comparisons, what I guess I'm trying to say is that they're actually good comparisons for your technique, because it might work better in one than the other, and you might get different results.
No, that's a good idea, and we have been collecting airborne data over that rock glacier over the years, and Bernard has been asking me to look at that. but there are so many other things that are going on, so I couldn't find time to look at it. But that's definitely in my to-do list.
Great. And you know that there's a paper on it which has some rates of movement as well.
Oh, okay.
It was written back by Stuart Harris, and I think his name is Blumstogel or something like that. It's a really weird name, but there is a publication on the one in the Slims River Valley. If you don't know it, I can send it to you. It's in one of the proceedings of the Permafrost conferences.
That would be great. I do not know this paper.
Yeah.
No, I have noted it down, so I will look for it. And in case if I don't find it, I'll speak out.
Okay. Anyway, thanks for the nice presentation.
You're welcome.
Hey, Usman, thanks for the presentation. It was good.
You're welcome.
I just had a couple of general questions. On slide 5, maybe I misunderstood what you said, because you're comparing InSAR and optical. And you're saying one of the advantages for the InSAR was to see through foliage.
Yeah.
I wasn't aware that it could do it. Is there a particular processing technique, or I thought we needed LiDAR to do that?
No, SAR by itself, like it depends upon the frequency. So if you are operating in lower frequencies, that can penetrate through foliage pretty easily. It's inherent feature of the EM waves.
Okay, well, that's good to know. I think it was on slide 19. Mm-hmm. You had for your DEMs, I think like the differences were about, I think they're in the order of 50 plus or minus 50. I think it was slide 19. Is it?
Yeah,
sorry, yeah. So the differences between these approaches were about 0.05 meters. Is that also representative of the levels for when you're looking at differential ground movements in terms of between optical and also InSAR, in terms of levels that you can achieve?
For the FODAR, it is of the similar order, like submeter, like down centimeter scale. For the radar, it is of the order of the wavelength. So for the L-band, it would be again like in orders of centimeters.
Okay, so they're both comparable in terms of that resolution.
Yeah.
Okay. And what was the relative difference in processing time between the two approaches?
So for the FODAR, generally, if you're processing the data at the highest resolution, it takes around a week to process. Right. Whereas for the InSAR, now with the time domain back projection algorithm being implemented on the GPU, it's embarrassingly fast. So it's like within the order of like minutes, you can process the images, and within the order of like an hour, you can generate some cool results.
Okay, and is that because the software itself is available for the GPUs versus the optical?
Yes, okay. Yeah. So it's being implemented on the GPU, and then otherwise time domain back projection algorithm on a regular processor is not possible. Right. Because the data is not tractable. It's like super big, super huge.
Yeah. No, it's a great study. Thanks.
Yeah.
Fantastic presentation. Thank you very much.
You're welcome.
I'm sure if anyone's got any other questions, they can get in touch with you. Once again.
Thank you very much.